So the second half of polymers is now condensation polymers. These are the syllabus statements. You can pause on that if you want to. A reminder about addition polymerization. We have a monomer that repeats. Usually it's an alkene, and when it bonds, it forms that long chain, which is a polymer, and the monomer is usually a small molecule alkene, and the large polymer is a much longer chain solid. This is how it works with the condensation polymerization. We have two different monomers, and they're arranged in an alternating fashion, and when they react, they form an alternating chain. That's condensation polymerization. Let's have a look at how that actually works. I've shown this in a bit more detail. This is monomer A, monomer B, A, B, A, B, and they're arranged in an alternating fashion. Here I've shown exactly the same molecules, but I've shown the bonds. This is a reactive end of the molecule. So this bit here is the unreactive bit, and we've got a reactive end. Same with monomer B, we've got a reactive end. What happens is, as it reacts, that bond between the unreactive part and the reactive part, that breaks. And you can see that happening on all of them. Then what happens is, this bit here and this bit here move towards each other, and they form a smaller molecule. These two, meanwhile, join together with a new bond. These two join together with a new bond. These two join together with a new bond. Okay? So overall, we have this reaction here. We've got monomer A with reactive ends. They're the same ends on either side of the molecule. And then here, we've got reactive ends on this monomer B. And what happens is this bit here and this bit here join to make a byproduct. This bit here joins with this bit here, which joins with this bit here, and so on, to make this long chain, and that's your condensation polymer. Let's have a look what that looks like in relation to actual molecules now. So what we've got is monomer A, and this functional group here is what's called an alcohol group. You should know that. Here we've got another alcohol group. That's called a dialcohol or a diol. This happens to be ethane diol. Eth, meth, eth, we've got two carbons with an ol here and an ol here. So that's ethane diol. We've also got ethane dioic acid. So here we've got eth, again, two carbons. You should remember COOH is a carboxylic acid group. So we've got a COOH on one side of the molecule and a COOH on the other side of the molecule. Ethane diol, ethane dioic acid. Ethane diol, ethane dioic acid, and so on. Remember plus dot 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 plus dot dot dot. And what happens is it produces this molecule here. We'll have a look at how that happens in a moment. Now you'll see here that we've got H and H and an O. This bit here is the reactive part, and that reacts together. You've got the same here and the same here, and that would continue. So the idea is this bit here and this bit here are going to react to produce your H2O. This oxygen then bonds with this carbon. This oxygen has bonded with this carbon. Over here, this oxygen bonds with this carbon. There's my new bond. Over here's my oxygen, and it's got a new bond to this carbon. There's my new bond. And essentially what we've got is this structure here, which again, bond dot dot dot, bond dot dot dot, that goes on. So we've produced here a polymer from monomer A, ethane diol, and monomer B, ethane dioic acid, and at the same time, we've got a byproduct, a product that's been produced as a side product, something we're not particularly interested in, and that's water. You remember from your work on esters, the COO link is an ester, is an ester group. So what we've got here is an ester link in our molecule. There's an ester link here in our molecule. There's another ester link. There's another ester link. It shouldn't surprise you that we've got an ester linkage because we're reacting an alcohol with a carboxylic acid. And you should know when you react an alcohol with a carboxylic acid, you get that sweet smelling ester. This is now a polymer of an ester. And of course, we're going to call it a polyester. Okay, so all kind of links together, hopefully. Here's the structure of the condensation polymer when propandioic acid and methane diol react. So methane, diol, methane, two ols, there it is. and propane dioic acid. Prop has got 3 carbons, 1, 2, 3. We've got an oic acid on one side, and it's dioic acid, so we've got an oic acid on the other side. And again, what we've got is the H and the OH come off. If that H2O comes off, this oxygen is now bonded with this carbon. If this H here and HO come off, this carbon is now bonded to this hydrogen. And that's what you see here. So this oxygen is here, this carbon is here, here's my new bond. This oxygen is here, this carbon is here, this oxygen is here, there's my new bond. So again, what we've got is a polyester, but when we compare it to our previous polyester, it's got a different number of carbons. So this would be a slightly different polyester with slightly different properties. But that's essentially the way that the polyester works. Remember, of course, we end up producing water as a byproduct of that reaction. Okay? You might want to have a go at working out a similar scheme for different diol and a different dioic acid. Maybe try propanediol with ethanedioic acid to see what kind of structure you get. You need to know that some polyesters, known as biopolyesters, are biodegradable, and that means they can be broken down by bacteria or enzymes. They form smaller molecules, and I guess the question would be, presumably, that would be a way forward in terms of the environmental impact of polymers. Here's the syllabus statements. You should be happy with all of those. Hopefully that will make sense to you.